So I think in this talk, I'm going to try and cover the following topics. So the first will be so the Cartesian transition D3, D5, NS5 brain systems, orientals, and see some stuff about partitions and its collapse. And then I'm going to talk a bit about quivers corresponding to minimal slices. So I guess in the orthosymplectic case, you can find some, but it's still there's still a lot of work to do here because there are others that need to be kind of found. And then there's also, in these cases, we have, in particular orbits, the presence of a canonical quotient, which is different, well, it's certainly different from the kind of the unitary case. We can read this from the partition, I'll talk about that. And it's also like there's some kind of idea that it will be present in the brain system. And then perhaps in cases where subtraction works. And maybe also just talk about some slices that have been found from 60 theories in brain systems. So,
by the way, just for the convenience, it is De Leon online. Just for his convenience, I'm going to cut out a part of this board, which is sort of glare. Let's see if that's a good. They can't read that part of the board.
Okay.
Roughly speaking, yes, maybe slightly smaller than that, but yeah, they can't read. We try to go around that.
So the Cartesian transition was initially developed for D3, D5, and S5 systems, kind of corresponding to unitary quivers. So we could take something, for instance, I'll explain what this is. So we might have so these are D5 brains, these are D3 brains, these are NS brains, and we can basically suspend the D3. So we start off with this phase, we then suspend the D3 like this, we kind of send them to infinity along the NS brains, and then we can do Hanani-Witten transitions and end up with this. And we can keep on going, and that would correspond to something like it's the Coulomb branch of these quivers, and this is kind of a general quiver subtraction, which has been done quite a lot. And we can read off some identification. So we'd have an identification between singularities and the kind of brain systems that we can read them from.
the Kraft-Procesi transition. So this is, what is it that you're saying here? Reminding us about brane configurations for the unitary quivers?
Yeah, so this is just, we haven't got, this is before oriental. We're just talking about kind of the, I guess, the basic construction in unitary theories.
Okay. And
okay.
this is Hasse diagram here for
Yeah, so this is for
the quiver you wrote, or
yeah, so the SU3. So we've got the maximal here, and then mil A2, and I think we was talking about this sort of subtraction a little while ago. So I'm just that's just kind of a bit of, I guess, kind of the unitary background.
So you're writing down the Higgs or the Coulomb?
So this is just the Coulomb branch of
Coulomb branch. Oh, 1, 2, 3, but that's not the same as the one that you drew, though, is it?
Yeah. So I guess I was doing it on the. So I had the D3 brane suspended between D5 branes. But it's we by doing kind of changing the phase, we can go from one system to the other, and but yeah, this is just kind of a quick example from the unitary case.
I guess the system that Sam drew is the same as the quick subtraction that we were talking about when I was.
Yeah.
And it's just a stringy realization of the same quick subtraction.
Okay, so
a stringy realization of the same quiver subtraction.
Yeah.
You mean in terms of branes, or
yeah? Then the branes, what Sam just did is the same thing as the quick subtraction you do.
We were doing it in terms of quivers, and now you can do it in terms of branes.
Yeah, you can do it in terms of branes, and so I guess I'm going to talk a bit about this, but it also gets, there are a lot of particular sort of maps you have to use between partitions, and it can get a bit complicated. So I'm gonna give an example, but I'm also just going to be kind of, I guess, recapping a lot of the stuff that came from the second Kraft-Procesi paper. So now I guess the next step is to introduce kind of orientifolds and how we kind of read things off the orientifolds. So let's start off with so I guess in the second Kraft-Procesi paper, there was D3, D5, NS5, and then we have O3 orientifolds, and then we've got O3. So I've written N here, but we can take N to be 3. So O3 plus, O3 minus, O3 plus tilde, and O3 minus tilde. And so these we can. So right,
so N is a number here. Then you think it could be any number.
I can check. I can say this is just 3.
But you could do other numbers, you're saying.
Yeah. So so we could have it more generally. And so I guess I can kind of do it. But let me write down.
And these letters are talking about the type of the group, you're saying. So for every vertex corresponding to a group of some orthosymplectic group, you have a corresponding brane you need to add, you're saying. Maybe more than one brane. It's analogous to when we had the three-dimensional branes. You had for a vertex with a GLN or UN, you had N D3 branes, and now instead of that,
the orientifolds change. So now they kind of, I guess you can think of, they introduce more conditions on the open strings, and therefore you read off a different gauge group. So this is just, I'll just kind of give an example as to how you'd kind of read this off. So this is another brane system that we have. Right, so these horizontal filled lines are D3 branes. These are NS5 branes, these vertical filled lines. These crosses are D5 branes. And then in this is a bit different from what I had before. I've now got kind of along this kind of the center, these horizontal lines, and they correspond to the orientafolds. And so in the kind of notation I'm going to use is that a horizontal build line will be O3 minus tilde. I'll draw no line for O3 minus, and then for O3 plus and O3 plus tilde, I'll draw a dotted line. And the reason why we kind of don't need to distinguish between O3 plus and O3 plus tilde when we write it down is because when these orientafolds hit an S5 brane or D5 brane, they change. So in this case, we've got, let's say, I'll just say an NS brane changes from plus to minus and minus to plus, and a D5 brane changes from the untilded to the tilded and vice versa. So in this case, we've got nothing here, so we've got a minus. We then hit the NS5 that's from plus. We now hit a D5, so the orientafold here is now plus tilde, and it's going to keep switching between plus and plus tilde until we get to plus tilde here. We now hit an NS5 brane again, so this becomes a negative tilde, plus tilde, minus tilde, and then plus tilde again. So you can, it kind of becomes clear whether it's plus or plus tilde just from looking at where it's come from on either side. Okay. And okay, so for partitions of B, C, and D type algebras,
What limit does this weight system correspond to?
so this is so we can read off this quiver from here. And how you do that is okay, so I've said, yeah, should have explained this. So this kind of key is how you read off the gauge nodes from the brane system. And so what I mean by electromagnetic, so if you've got your D3 brane suspended between NS5 branes, then the presence of an O3 minus orientafold tells you to read off something with B type. So here we've got B0. We've now got a plus tilde here, so this tells us to read off something C type, and we've got one D3 brane between them, so we read off C1. And we now have minus tilde again, so we've read. And then now we see we've got a kind of more complicated case here, but we kind of see that on each far side here we've got plus tilde. Well, sorry, no, we've got plus here and plus tilde here and plus there, and so from this we've also got so, and if we have two D3 branes suspended between the NS branes, then we can read off C2, and then these D5 branes also give us a flavor of B2. And if I was to change the system, so then I had D3 branes suspended between D5 branes, then I'd use this side of the key, and I'd kind of do the analogous thing. I'd read off the quiver.
How do you determine from the left-hand side is the dashed line corresponding to plus tilde, not plus, also plus?
Yeah, so when we there's also a convention. So I've written down here, this is the maximal. So this is an example I guess we're going to look at in a bit. And so there's a convention usually will specify what is on the right-hand side. And then we can go through our rules and then whatever's, determine what we kind of end up on the left-hand side. And so if we want to write down brane systems that correspond to theories whose moduli spaces are particular Nilsson orbits, then part of our convention and part of what we specify, which I'll talk about in a second, is specifying what orientable we start with on the right-hand side.
What is the convention for we start with?
So here, we've started off with O3 minus on the right-hand side, and then we can just follow the rules and, it changes. But I'll in a second, I'll talk about kind of the,
But we always have to have something, there's nothing written, it's O3 minus, so we have to always have.
yeah.
You can't just have some between two branes, there's nothing. There's no oriental fold at all.
No, yeah. So if
in this situation, when we're dealing with what are you calling it then? Like a orthosymplectic gauge theory or something, you have to always have between every pair of branes some oriental fold.
Yeah, if we introduce O3 oriental folds here, then if I've just got NS5 and D5, then it's just going to switch between these four places.
The way it switches depends on, right? So for the D5, we're switching it between with or without the tilde plus, the plus with or without a tilde.
Yeah.
And within an NS5 is switching between the plus and minus.
Yeah.
But how do you know whether it's O3 minus or O3 tilde minus? I don't see any O3 minus except at the very right?
Yeah, so we start off by kind of part of our input data will be to say that we have an O3 minus on the far right, and then when it hits an NS5, it will change into an O3 plus. It hits a D5, O3 plus tilde, plus tilde, plus tilde. We can switch, because.
Oh, I see. Because it ended up plus tilde, that's why it became minus tilde.
Yeah, so then we've got another NS5 right here, so now it's minus tilde, plus tilde, minus tilde, and then plus tilde.
Okay, so somehow the way we're writing this, the electric and magnetic quiver, which is the quiver which we're usually writing down, corresponding to these brane configurations being in the Coulomb branch. Which quiver is that? Is it the electric quiver or the magnetic quiver?
So I've written down here so it's the Higgs branch of this quiver, which corresponds to the maximum SO5, and then from that we can kind of write this down. In this phase we've got the D3 brane suspended between NS5 brane.
So this is the quiver where the vertices correspond to being between NS5s, right? Then, right?
Yeah.
And that's the ones for which the brane figures we're looking at are the configuration in the Coulomb branch of this theory, right?
So we can read off the quiver from the branes, but in a minute we can then move to the phase where the D3 branes are suspended between D5 branes, and then
but being suspended between the NS5 is what's usually considered the Coulomb branch. Right?
Yeah, so this is
representing
just writing down a brane system who I can then move to the Bennett between.
It's not the right way.
What's it?
You have a brane system, and then the three branes could either be between an S or between D5.
Right.
Okay. If it's between an S, you call it Coulomb branch, and if it's between D5, you call it electric quiver, and if it's between D5, you call it magnetic quiver.
Between D5, you call it magnetic quiver. Between NS5, you call it. But
now, whether you are interested in the Coulomb branch or the Higgs branch, that's a choice. What are you after?
But for the electric quiver, then the brane figures we're writing down are the Coulomb branch of that electric quiver, right?
Yeah, but
and the Higgs branch of the magnetic quiver. Then
electric quiver has both Higgs branch and a Coulomb branch.
That's true, yes. But the branes that we're looking at here are vacuum states in a Coulomb branch of the electric quiver, right?
Yeah.
Motion.
What do you say?
Yeah, I mean the brane motion corresponding to the Coulomb.
Yes, you're right.
Okay, this is what I wanted to make sure about. But
So then I can write down, I can do kind of transitions to then write down the phase where the D3 branes are suspended between the D5 branes. And then I can do estrality and then read off the quiver whose Coulomb branch corresponds to maximum SF5. So, okay, so
But did we clarify the point or is it more little green? So but once I compute the figure, it has both Higgs bound and a Coulomb.
that's correct.
I
Yes.
just need to interpret what it is. If I want the Coulomb one, then it's an arrangement of the branes in a certain way, and if it's in a Higgs branch, it's the other way.
Right. Agreed. So what could happen in general, right, is you have a brain configuration which gives rise to an electric quiver, but maybe it's not clear how to get a magnetic quiver out of it. Is that right? You have a brain system, or is it just given a brain system you can always get both an electric and a magnetic quiver?
You have conditions that the number of levels will be large enough, right? Because so given a brain system, there is a question whether we can move to the situation where they
Right.
can end, if all of them end on an S,
Right.
can it move to the situation where all of them end on D5? If the answer is yes, then the first you call electric quiver, the second you call magnetic quiver.
Okay.
And each one of them would have a Coulomb branch and a Higgs branch.
Right. Exactly. Okay. Yes. But so basically, when we're writing pictures like this, we always have an electric quiver. And if we're able to do this annihilations and creations sufficiently, then we have also a magnetic quiver.
Yeah.
Okay.
okay, so yeah, and so for partitions of B, C, and D type algebras in general, we can only find quivers whose Coulomb branch corresponds to a special Wilson orbit. So I'll just
Now, maybe I should note that the way this it looks a little bit strange, maybe, but the way that these table of B, D, C, etc. are set out, it's so that when we're doing electric quiver, we change vertex at the NS5, and the NS5 we're swapping between plus and minus. And so if you look at the electric quiver, what happens between plus and minus is you go between symplectic and orthogonal groups, and then the same thing for the magnetic quiver between the for the D5 branes, between the tilde and no tilde. So you toggle between whether it's, so B and D are both orthogonal group, right? And C is the symplectic group. So D and B, it's a little bit harder to distinguish, but that's just whether you're even or odd dimension. You cannot have this choice for C, it has to be even dimension.
Yeah, I guess this is also kind of a thing under, so when we do the estrality, we're swapping D5 and NS5 branes. And then we're also, it has a operation on the orientifolds as well that we have to, and that's kind of this between, we're swapping O3 plus and O3 minus tilde orientifolds.
I see.
So whereas if we don't have orientifolds, we just have to think about swapping D5 and NS5 branes. But now we've got orientifolds, we have to think about this too.
Also, you have to change the three branes. Okay.
So these two, the O3 minus and O3 plus tilde remain the same, but it's the O3 minus tilde and O3 plus we have to change.
Okay.
Okay, and so yeah, so we say that an orbit is special if it's partitioned the Lustig-Schwarzschild map by kind of twice gives partition again. And I guess just well, another piece of terminology that we kind of sometimes use is that for partitions of D type, we can end up with very even partitions, which is when we have in our partition, it's fully made up of even numbers and they all occur with even multiplicity. I don't think I'll be kind of speaking about that much more, but yeah, it's kind of another complication in a few cases. Okay, so I guess I'm gonna.
So the point is that I don't remember what this DLS is, but the point is that there's some formula here that's telling you from a partition, and now this partition is the partition for odd and for symplectic or orthogonal groups. So it's what is it? It's like a pair of partitions or something. Anyway,
yeah. So
you have this operation which tells you whether your orbit is special, and now orbits or partitions, which are labeled by partitions for these classical groups, classical Lie algebras, correspond to certain brane configurations. You're saying.
So yeah, we can go from the data of the partition to then reading off to then a brane system whose Higgs branch corresponds to that
Nilsson orbit closure.
So I've kind of this is what was going on here. So we could take something for Maxwell SO5, and then we could read off the brane system whose Higgs branch corresponds to the Higgs branch of that theory.
So every nilpotent orbit closure in classical Lie algebras corresponds to a brane system.
Well, so I guess we have to kind of be careful in some cases because I guess part of the difficulty with a lot of this subtraction is that for some orbits we can't write down quivers whose Coulomb branch corresponds to that orbit.
Right.
So we have to just
but that would be saying that we can get all of these orbit closures as Higgs branch of some electric quiver, but not necessarily able to get a magnetic quiver for that. So you can't write it as Coulomb branch a priori.
Yeah, so in the I guess I might speak later and write down some kind of Hasse diagrams, and for some we'll just have to leave it blank. And this is also a thing with so part of the motivation behind quiver subtraction is that you want to get quivers that correspond to minimal orbits. And for at least at the moment for orthosymplectic quivers, something like a minimal B type, you can get next to minimal, but you can't get minimal. And again, for C type, you can get next to you can't get the minimal. So it's those are kind of related. I mean, we'll probably maybe talk about it a bit further on, but those are related to the minimal. There's a simple kind of step you can go from minimal D type to minimal B type.
Okay.
But yeah, anyway. So maybe I'll take this off. So yeah, so in general, it can be quite fiddly to kind of work with these partitions, and we can I guess I'm just going to give kind of an overview of going from partitions to reading off brane system. So we introduce the Barbash-Bogan on a partition, which, depending on what the orbit of the particular type of algebra we're looking at, different. So, okay, T is just transposing the partition. This net minus and plus here, I've written are just kind of
What is BV again?
Barbash-Bogan.
Oh, right, Barbash-Bogan. Okay.
So what this does is so if we start with lambda as a partition of some B type, then we can transpose it. Then this minus will turn it into a partition of something C type, and then we can do C collapse. And I'll kind of just explain briefly what those things are, and vice versa with a partition of something C type. We can do this plus transition, which turns it into a partition of something, B type, and then B collapse. For the A type, it's much simpler. It's just transposing, and for D type, we just have to do this thing called D collapse.
So I want to raise some point here. You have three operations in this. There is the transpose, there is the minus or plus, and then there is the collapse. And there have been several definitions in the literature with different ordering. And different people have different ways of doing that. And so the first question is there a correct one, the one which is most useful? And if it is useful, then useful for what? And another question is, what is the discrepancy if you change those orders? So to me, it's not clear. For example, if you change the order of transpose and minus, what's the partition which will give you different results?
It's not going to work. You have to do transpose first.
Because
the partition is not a good partition for the type that you end up with.
Okay.
And therefore you have to adjust it.
But there is a definition by Achar. Let me find what it was. I need to be specific about the ordering. But go ahead while I look for the famous.
Okay. So these just operations are very simple. It's just adding one to the largest part of the partition and subtracting one from the smallest. And then this C, D, and D collapse, again, it's not very difficult. It can just be a bit fiddly sometimes. So I guess I should have also said yeah.
So lambda is a priori just one partition here.
Yeah, so lambda is just some partition of whatever algebra we're looking at.
And for the B, C, and D type, what's the condition on lambda again then?
So yeah, so for B and D type, we require that.
Okay, fine. So a char does minus, then collapse, and then transpose.
There are big other ways. First,
I couldn't understand what you said.
It's two different sectors and write it in different ways. And in the literature I read in the brain and the transition and the literature by Neoput and Always and the other about their definition are also different. So I checked that they are equivalents.
All partition.
Yeah.
So just I guess another like to main so it's part of the what we kind of require to keep things special. So for partitions of B and D type, so just SON, we require that the even parts of the partition, so for instance, so the even numbers that occur in the partition go with even multiplicity. For C type, we require that the odd numbers that appear in the partition go with go with even multiplicity. And so this C, B, and D collapse is doing exactly this. And I guess I can kind of give an example. So they all pretty much work in the same way. So if we had something like, let's say the partition of 3, 3, 2, SO8, then we see that this even part here 2 occurs with odd multiplicity because there's just one of it. So what we do is we replace 2 with 2 minus 1, and then we add 1 to the first occurrence of a number in the partition that's less than 2 minus 1. So in this case, this just becomes 3, 3, 1, 1. It's I guess it's just something to. It's not particularly difficult to do these sorts of collapse transitions, but it just all gets a bit fiddly when you've got to do one thing after the other. And it's so it's the same thing for the B and D collapse, essentially working the same way, and the C collapse is the same. So if we have some odd part that occurs with even multiplicity, then let's we subtract 1 from one of those parts, and then we add 1 to the next thing that's smaller than what. So it's I guess you can just kind of write a code that does it.
So you subtract 1 from one of the parts that occurs with odd multiplicity, you say, and then
and then you add 1 to the thing that turns up the next thing that's smaller than what you've got.
I see.
So here we've gone 2 minus 1 is 1, and then I can imagine there's lots of zeros here.
Add 1 to 0. Okay.
Okay.
That's the collapse. Okay.
Yeah. And there's kind of a brain realization of this as well. Okay, so I guess
So you have this operation on partitions. You say that you're modeling here.
Yeah, and then I'm just going to kind of specify this just to show that how you do it, and then I guess we can go back to that example that I gave and kind of work through that. So we can define a brain system whose Higgs branch corresponds to equivalent whose Higgs branch corresponds to a particular Nielsen orbit. So for Bn, so we set NS, ND. So NS and ND are the number of NS brains and D5 brains, respectively. This LD is the linking number for the D brains, which is, we can define as there's an extra thing we have to take care of for these oriented poles. So generally we define the linking number like that. And if it was all unitary, then if we're just considering D3, D5, and S5, then that would kind of be the end of it. But when we have oriented poles, we also have to consider the oriented pole charges. But it's not much more difficult. And the linking number for the NS brains is exactly the same, but then it's the number of D5s on the left. So I guess the reason why we have the Barbach-Bogan map to begin with is because it tells us how we can find the linking numbers for the NS branes. And I've written down another kind of operation here, even, which is kind of yet another thing you have to do. And it's, I mean, I guess I can give that's the, write it down. So the,
I'm just trying to understand what is happening here. So first you gave us this picture with the brain systems and the electric and magnetic quivers, and now we've moved to nilpotent orbit closures. And I guess the goal was to try to develop some version of quiver subtraction, as you want to try to understand the stratifications of these nilpotent orbit closures. And of course, we know something about this already because of the all this combinatorics of the pose set, I guess, for the nilpotent orbit closures. But you want to try to recover it from, I guess, you want to construct brain or quiver operations that recover that. Is that the point?
Yeah. So I guess the idea is we want to go from understanding the nil cones to then finding the sort of, we can work out quivers that correspond to each leaf.
Okay.
And then understanding kind of what quiver subtraction should be.
The EDs, now you have these parameters, which I guess are imitating some parameters we had doing quiver subtraction before. I don't remember what those parameters were, but so we have these numbers of D3 branes. This ED is somehow an important number that you can assign to every vertex. And right, so ED is assigned to the vertices of the electric quiver, or?
So yeah, so well, it's assigned to the NS, the linking numbers of each NS brain or each D5 brain in the brain system, and then depending on what's suspended.
And this D Barbash-Vogen. So I understood that D Lustig-Spaltenstein was supposed to be telling us whether or not we were special. That's what you're saying. I don't understand exactly. But you wrote a formula for DLS, and so there's this subscript of X there. So you take the transpose, and you have the subscript of X.
Yeah. So this X is meant to stand for C, B, or D class.
So you have to do that. So if it were just transpose, then I guess the square would automatically be lambda, but because we're doing something else. Now if you do this operation, okay, for this one it's fine.
This is always, yeah.
So now you have DBV. So DBV is not the same as DLS, right?
Yeah, so we have these extra
plus and minus.
Yes.
And what is the point of the DBV? Is that something a refinement of this LS, or what is the DBV giving? What's the property it has? It's no longer telling you whether an orbit is special. Or...
DBV, the Barbash-Vogen insists on taking the dual non-length dual, whereas the Spaltenstein doesn't.
I see. The DBV is taking the Langland's dual, so it's going from an orbit closure to an orbit closure of the Langland's dual. Then.
Yeah, so we need to have, when we work with House diagrams, we need to have the B equals C together.
Oh, I see.
All others, we don't have this feature.
So for Lustig-Spaltenstein, it doesn't do that. It's just staying on the same type. Whereas what we want is to do Langland's dual. We want this to correspond to some, mirror symmetry or some symplectic duality or whatever. Right?
Yeah.
Right.
So this Lustig-Spaltenstein map, if you take a partition for a few-type orbit, Lustig-Spaltenstein, the X is a C or is it a B? It's a C.
No, it'll be a B because
Okay.
yeah, because the reason this is a C is because
So you're doing
we've done this. So this changes the partition into, you know, a partition of n into a partition of n minus one. And this changes it into a partition of n plus one. So if we weren't doing this, then it would have to be the other way around. But because we're changing the partition, you know, into a larger one or a smaller one, we then do a B collapse, even though it's, you know, we start off with something, a partition of something C type and the same the other way.
Yeah. So whenever you have this plus minus operation, you are moving from B to C or vice versa.
And so I mean, you know, I'm just presenting this here. Even and odd are like more kind of just a particular way of changing the partition. And so I guess we can do an example, which is the one I just rubbed off.
Sorry, Sam. So just to go back to Ami's question about the ordering. So then it appears that you have to do minus, and then you do the collapse of the dual thing first. So it's always minus and then collapse of the dual, and then the transfer thing would be before or after. Yeah. But then if you wanted to do the collapse first, then it's the collapse of the same. Then you do the minus, and then you can do the transfers. Or is it always the collapse
is needed to fix what you had from the
transfer? So it's always okay. I see. So it's not just any order; it's always minus collapse transpose or the transpose minus collapse.
Yes, transpose should come first. And then the question is, what do you do first? The minus and the collapse, or the collapse and
Yeah. So okay. So I guess the thing I want to highlight here is that this is related to the question we had earlier. Part of specifying how we get, you know, how we read the brainstem from these partitions is to say our rightmost or so if you know, if we're looking at something dn, which is what I was doing with SO5, our rightmost orientable plane is O3 minus, and we specify that, and then we can just go through and find all the others. You know, for Cn, we say the rightmost is O3 plus tilde, and for Dn, it's O3 minus.
Right. Okay.
So that's part of the kind of, that was why in the rightmost oriented was O3 minus. Okay, so maybe I'll.
What is it? ED or ES? Or is it L?
L, sorry, yeah, that's meant to be
Okay,
L.
L's.
Yeah, so these are the linking numbers.
The linking numbers. Okay.
But yeah, I'll redraw that
And
example.
what is the NS and the ND again? Those are both.
So the number of NS is the number of NS brains, and ND is the number of D5 brains.
Oh, I see. Those are both equal here.
Yeah, yeah. Okay, so maybe I'll put back up the example we had.
Well, why do they have to be equal? Just this is the way it is. If you want to get a nilpotent orbital closure, we need to have them equal.
Yeah, I mean, why are they equal? Why do they have to be equal? The number of NS and D5 brains.
Is that true in the type A as well?
Number of NS and D5?
It doesn't have to be, no, but we're talking about, I assume that the idea here is we're talking about what's required to get a nilpotent orbital closure, or
yeah, it's possible that for nilpotent orbits you have the same number.
So in this case, we're saying for B, C, and D type nilpotent orbits, it's the same number of NS5 and D5 magically.
Yeah, if you start with the nilpotent cone, you get the same number. The thing is that as you perform positions, the number does change. So even for nilpotent orbit, I don't see why they should be the same.
This is just the nil cone.
For the nil cone, you have the same number.
Yeah.
It's just that's how you could start a quiver. Quiver has the same number of nodes as the number of fermions.
Okay, so if we go back to what we had earlier,
Even though there is a problem with one of the either the B or the C, because there we just don't know how to compute. Right, there is this case, which one we don't know how to compute?
What, sorry, for your C?
It's either B or C. Okay. It's they just write down the proposed quiver for the code, but you cannot compute the complexes.
Oh, off the top of my head, I can't remember.
Then there's no point. You write a quiver, but you don't know how to use it. So then what's the point? And so you could write whatever you want. As well. If you don't know how to compute it, then there's no.
The Hilbert series you can compute for a Coulomb branch of a quiver, right? Normally, the monopole formula.
But you get into a situation where there is a critical number of labels, which makes the formula divergent.
Oh, I see. Okay.
Like so, take the case with C1 with
Okay.
C1 with O4. We use this and get the divergence. So each time C1 has local has 4, then we don't know how to compute. I think O1, C1, and framing O3. So the C1 will have 4.
I see.
That's the okay. So now I have the answer. So the answer is for C type. If you try to write down the code for C type, the quiver that people are writing down is an alternating sequence of AC, like this one, and this one has a so it's precisely what some hold down. This thing, this quiver. The C1 has divergence, and the C2 also has divergence. So B1 will give you 3, B2 will give you 5, in total it's 8. That's 4 times the group. Each time you have precisely 4 times the rank, you have divergences in 4. Okay, so this is the some people claim that this is the quiver for the Newton problem of type C2. But there's no real evidence for that.
Because so it's supposed to be the Coulomb branch of this quiver we're saying, but the monopole formula diverges, so you have no evidence.
And so you need something else. If you say, and so we've seen this before, that monopole formula diverges, but nevertheless you could make a claim about the Coulomb branch. Right. If you could argue some alternative way, then at least we have this, but we need to see.
Is it clear from the brains why this happens? It's not. It's just when you plug it into the monopole formula, it diverges. This is.
It's some in the simplest case, you get a situation with we should look for balance. Check the balance.
Okay. So if we want to read off, so
So you've done an example of maximal SO5 you're seeing here.
Yeah. And so, in this case, if 2n plus 1n is 2, and we can read off from here, but it's kind of what we get. And this is a bit less easy to see, but it's comes out. Okay, and so the next step we kind of want to do is to do transitions and move to a phase where D3 branes are suspended between D5 branes, which I don't know how. Yeah, I guess we can start. So maybe I should rub this off. Okay, so in general, if we don't have orientifolds like these O3 orientifolds, then Canonic-Witten transitions are it's going to be kind of fairly straightforward to use them. When we do have these orientifolds, how you get those transitions in the first place are considerations about linking numbers. But I mentioned earlier that these orientifolds contribute to the linking numbers, and so we have to be careful as to what transitions are allowed. Now, there are essentially kind of four, I guess, allowed types. So I might not have drawn it this way before. But... leave the.
Do you do a specific the brain system you drew is specifically for this maximal SO5, but then the quiver is electric quiver for this brain system, is that it?
Yeah.
And now where's the partition, or you write the partition, or you don't need to write the partition?
I guess the partition we start off with will just be the kind of maximal partition. And then when we follow through all these maps, we end up with it telling us what these linking numbers are.
What do we do with these linking numbers now once we've computed them?
So then we can use them to kind of read off I've kind of, presented it here as the example in one of the papers. So we can use the linking numbers to then work out what the brain system should look like.
I see. Here the linking numbers, LD is just the 4s. And where does that appear in here? This is a 4 between every D5 brain.
Yeah, so I guess
the linking numbers this oriented fold there.
So that was we had the kind of difference between the D3 branes as well as the orientifolds ending on the left and the right, and then we had a contribution from the number of NS branes on the left. So for each of these, we don't see any D3 branes ending on them from the left or the right. We just have these orientifolds. So plus tilde plus tilde plus tilde. But they're going to cancel out, and so we just see 1, 2, 3, 4 NS branes on the left, and that gives us the 4 in the linking numbers. So and what I'm drawing over here are they just kind of allowed sort of transitions that we can have. So these here are D branes, and everything that's kind of along this central horizontal axis are the orientifolds. And I guess it's a bit kind of we can go kind of step by step, but I don't know, it might take a while. But maybe it's just best to kind of write down what we end up with.
Again, how do we get these linking numbers? What is the relationship between these linking numbers and the range system now? How do we get the 4s and the 0, 2, 0, 2, 0? Let's just make sure that we understand. So the 5 and the 5 comes from having 5 of each type of brane. We have 5 vertical lines, we have 5 of these things. So can you just explain to me where do these 4s come into the picture here?
So these 4s are the linking numbers for each
Right.
of these D5 branes. And so when we defined it, it was the difference between the D3 branes on each side,
Yeah.
left minus right, I think. And now we've got orientifolds, we have to also take into account the charges they have.
Right.
But I think it turns out that, you know, we have nothing in, no D3 branes ending on these D5s. And the
Right.
difference between the O plus and the O plus tilde is 0. So we just have contribution from the 4 NS branes ending on the left. Sorry, not ending, but just on the left of these. So each of these D5 branes see these same 4 NS5 branes on their left. And so that's why we have 4 as the linking numbers.
The 4 NS5 branes, see,
Yeah.
they're on the left.
On the
So
left.
it's not just the D3 branes we're counting for this LD, it's also the NS5.
Yeah. And the same thing is kind of true.
For the 0, 2, 0, 2, 0 then, is that?
So these are for the NS branes. And I guess that comes from that's what the Barbash-Bogan map contributes to when we you know, we've got the partition, we do the Barbash-Bogan map, and then we have this other map, this even or odd, and then that tells us the linking numbers for the NS branes. So
I see.
okay, so this might
But you can't just tell us quickly how we get the 0, 2, 0, 2, 0 in this picture. It's not simple.
I mean, you can also read it off because it's going to be the difference between the left and right of the D3s and the orientifolds, and then you're adding on the number of D5s on the left. I think
none of these NS5s have D5 on the left except the last one.
Yeah, and so on the exact charges of all the O3 planes. Maybe you know, I kind of
Let's do it. I will calculate.
all right.
But
So-
then the one, and then the next thing would be, if we had it the other way around, if we knew what those numbers were, how do we then write the brain system? They're saying basically it's what you can do, but
Yeah, but given that it's a unique choice, so once you have the numbers, you could delete the brain system. Because it's multiple.
Right. So if we do, I guess I'll just write down. We can use these rules to move these D5 branes through the NS branes, and we end up with.
you can do annihilation and creation in order to help you find the numbers, you see.
So now I'm moving from the phase where we have the D3 branes suspended between NS5 to when we have them suspended between the D5.
Oh, you need to do that in order to write down the LS.
So in the next stage I want to do now is read off the quiver whose Coulomb branch corresponds to.
Oh, you want to find the magnetic quiver.
You're asking for the linking number.
Oh, okay. The linking numbers.
Without the moving brains. It's the rearrange them in configuration and completely complete.
Because I need to understand
These
how.
transitions are constrained so that the linking numbers stay the same.
Okay.
So that's why we have these 4 kind of transitions. So they're constructed so the linking numbers remain the same.
I see.
So okay. So and so yeah. So now we can also we can move to the phase where we suspend them between D5s, and then if we perform S duality, we can read off the quiver whose Coulomb branch corresponds to Maxwell SO5s.
So this quiver, the one you had here, it's Higgs branch, gave you this Maxwell SO5, and this was something then that was in Kraft and Procesi article, right?
Yeah, so yeah, sorry, in the paper, yeah.
That's the starting point. We have Kraft and Procesi's
Mm.
description. So Kraft and Procesi classified nilpotent orbit closures, right? in SLN and also in the special orthogonal and symplectic the algebras. And so that's, I guess, the mathematical starting point here, right? We have this quiver, which corresponds to some Hamiltonian reduction, which gives you a certain nilpotent orbit closure in SO5. And from that, you can write, so this, and from that, you can write this brane system. But now you want to go the other way around. You want to, from the brane system, you want to be able to write down the quiver and also find another quiver that interchanges Higgs and Coulomb branch, right? This is the point here.
And
right?
yeah, I guess, yeah, for quiver subtraction, we're kind of thinking about that in terms of the Coulomb branches of kind of on the Coulomb branch. And so I'm starting with something here. The idea is to then find the theory whose Coulomb branch corresponds to maximal SO5. And then you can kind of work out what subtractions are going on. And you can find, you know, the kind of general quivers that correspond to particular slices.
Okay.
Yeah, so I won't do kind of every step, but if we do, so if we kind of move to this other. So what it's telling us now, so these two lines here and two lines here are these D3 branes that are stretched between these two D5 branes. We've got another two D3 branes here and here.
So you're performing these annihilation creation.
Yeah,
no.
So I've moved these four over here and I've moved this one all the way through. And so then our Oriental folds are changing through here. Then we've got minus tilde here, and minus here. Okay, and then we can perform, so we can then kind of, you know, rotate into astrality, and so we end up with doing that. So we're almost done now, and we now need to perform the kind of brane analog of the collapse transition. And so what is the kind of brane analog? So the brane analog of the collapse transition says that if there's a half D5 brane connected to an O3 minus, and it can, so again, O3 minus, O3 plus, because we moved up ahead, but O3 minus, plus, minus tilde, minus tilde, minus tilde, plus tilde. So, okay, so
we perform these annihilation and creation moves to turn this original brane system into an equivalent one, where now we can do some interchange of type of brain to get another diagram looks like the original one and a new quiver. And that gives you from electric to magnetic quiver. This is somehow in the type A case, where there's no orientifolds, etc. This operation, I guess, is mathematically just taking the transpose of the partition. But the advantage here is that we don't have to have a partition. We can do these brain moves when there's no nilpotent orbit closure involved.
So what this is saying is if there's a half D5 brain, so now I'm talking about half D5 brains, we're calling them half D5 brains or half NS5 brains because the orientifold changes across each side. So I can just say kind of D5 brains or NS5 brains. So this collapse, what we saw earlier was kind of decollapse. In the brain system, it's saying if there's a D5 brain connected to an O3 minus, which we have here, and can be pushed through an NS5 brain, so the NS5 brain is now connected to the O3 minus instead, then perform that move. So if we do that, we then end up with.
And a half means it's on the symmetry line in the middle then, right?
Yeah, it means that, yeah, so the O3 planes are is changing across the NS or
In the picture we were having here, all of the brains were 1/2 brains.
Yeah, so I guess I haven't mentioned this thus far, but it's always been the case. But I guess we don't necessarily need to put half D5 or half NS5, but it's been this way throughout.
But we're imagining that the symmetry that we've taken this quotient by is flipping across this horizontal line. Is that it?
Yeah, so these D3 are again kind of reflected in the orientifold.
To the other ones, yeah.
Yeah.
So it has to be symmetric across this horizontal line.
Yeah. But that's exactly what we've done here. So we've moved this D5 across. Now it's not talking to an O3 minus. Yeah, okay. So we can read off. Okay, so let's just write these on. We can use the same rules that we had before to read off now the quiver we get here. And so it's the Coulomb branch of this quiver which corresponds to maximum SO5. And okay. So maybe it's
and now we'll see probably that this one is possible. The C node has enough labels.
how are we doing the time?
We should go to lunch.
No.
But I just wanted to make sure I understood here. So now collapse is just a brain.
Yeah.
It's just one of these annihilation creation moves.
Yeah, but you can see, so maybe importantly, when we have no orientifolds, if we're moving D5s past NS5s, we're going to create or annihilate D3s. But there's no creation or annihilation of D3s here because the preservation of the linking numbers is taken care of by the orientifolds.
I see. But now to read off the quiver, can you tell us how to read off this quiver from the brain?
Yeah, so maybe
so we know how we got this quiver. So I guess for the first one, it was relatively clear, right? It was just count the number of horizontal lines together with what type of line you have in the middle and look at your chart and you get the type of the group, CI, BI, DI, right? Now this one looks a little bit more complicated though, because we have this branes connected to D5s in the middle there, right? So maybe it's not more complicated. Maybe it's still the same. Just looks like it is.
Yes, it's like now the table that we had before.
We have to be careful because, like I said, it used to be in the type A case. So, yeah, you joined at just the most difficult time. It used to be like in the type A case, we had no of these lines in the middle, and it was just very simple. Just a number of horizontal lines gives you the dimension of the vertex, and the number of x's in there gives you the dimension of the framing, this number on the square attached to the vertex. But now it's more complicated, right? So now we have to know what type everything is. Yeah. So the prescription you had with this box, I thought that was for telling you what you had at the gauge node. So it's also telling you what you have at the framing node too.
So when I wrote down the box, that was just the input data for the rightmost orientifold. This table is telling us how to read the type of gauge group we get from the intervals between.
But that'll give us the vertices, right? Because then we do that together with counting a number of D3s, and that gives us a vertex. So this middle part gives you the type, B, C, or D, and the number of horizontal lines gives you the number, the dimension.
Yeah.
But what about the framing? So how did we know it was a C2 framing there?
Right, yeah. So, well, I mean, so this is coming from the D5s.
So normally 4x's, I would have thought we're putting a U4, you might call it, or GL4, but now you're not doing that. You're putting a C2, right? So
yeah.
How do we know that?
I guess it's part of the rules of reading it off.
When we do an orthosymplectic quiver, we have everything is B, C, or D. We don't have any type A, even on the framing.
I mean, I guess. Sorry, what was?
We're doing only type B, C, and D now. So all of the vertices, framing or gauge, are all B, C, or D.
Yeah.
So you count the number of x's, and then you sort of divide by 2 or something. But what's the type for the framing then?
C2. So I guess we can.
But why is it a C type? How do we see that?
We define the parameter n, which is defined as the sigma t, sigma transpose plus sigma transpose j minus sigma transpose j plus 1. It's mj equals sigma transpose j minus sigma transpose j plus 1.
You're answering your question in half an hour ago? Huh? But are you answering this noise?
Yeah, now the current is how do we read all the data?
Yeah. So I didn't understand though. It's like, it's a very concrete question, right? We have 5 x's here.
It's a B node, and so the framing is a type C. That's the simplest answer.
Well, yeah, I guess that has to be, right?
Yeah.
Because the D is always hooked up to C and never hooked up to B or D. But what if it were a C gauge node? Then how would we know if it was a B or a D framing? And
so here you need to discuss this point about the so-called Z2 anomaly. That the total number of framing, total number of labels.
Okay. But there's another thing, right? Like so here we're not supposed to count the x that's off to the left. We're only supposed to count the x's that are in there. And then that's supposed to give you the dimension of the representation, I guess, right? So we're getting a C2 corresponding to a 4-dimensional representation. If we were in type B or D, you could argue maybe if you had 5 x's, then it would be the B type. And if you had like an even number of x's, it would be the D type. Is that the point then? Yeah. Okay, so then we know.
We have to, we have to remember, I mean, we could have said we have 5 x's here, but we have to remember that we have, we've got extra things to do.
The Astra away from the orange report.
Yeah, you think combining them and moving them off.
Yeah, if you move them
together and
then you again get C.
And now once we've done this, it's easier than it looks like to write down this LS that we wanted before, like than it was in the original quiver. It seems like the LS is somehow, for some reason, slightly more difficult to read off from the from the original.
That's like, yeah, it's like-
Maybe we should get lunch then, and then we
Yeah,
can.
okay.
Otherwise, I won't have time for lunch.
Yeah.
You will have time for lunch, but I won't.